Okay, so I'm happy to be here today to introduce Professor Wasserman, who is visiting us from Cornell University. Ira has been my PhD advisor. So we've known each other and collaborated for a large number of years. Before being a professor at Cornell, he was an undergraduate at MIT. And after that, he did his PhD at Harvard University. And then he moved to Cornell University, where he had a bunch of fellowships, and then he became faculty there. And he has been faculty there ever since. Now he is the Kenneth A. Wallace Professor at Cornell in both physics and astronomy. He is quite well known in the field of neutron star physics, in cosmology, and he has done a lot of work that is well regarded by the scientific community. And we're lucky to have him here until the 23rd of May. So if any of you want to talk to him, you should make an appointment. And I guess this is it. Thank you, Ira, for coming. And what we'll talk about magnetars now.
Okay, thank you, Roxandra. So I should tell you, this is the first time I've ever given this talk. It's a longer version of a talk I gave at the Simons Foundation in New York. There was a meeting, and that talk lasted 45 seconds. So this is going to be a little bit longer. Get to it. So many of you probably have heard of magnetars. I just thought I would give you a little bit of history. They were first proposed by Chris Thompson and Rob Duncan, a student at Cornell before Roxandra's time. They have very strong magnetic fields, 10 to the 14 Gauss or larger. So those of you who've studied environmental science know that the magnetic field in this room is about 1 Gauss in these units. So this is 100 trillion times stronger. As a result, there's an enormous amount of magnetic energy. And so magnetars are a tremendous source of energetic phenomena. They've been proposed, and that's why I call it Deus ex magnetar, to basically underlie many of the most important and interesting phenomena in high-energy astrophysics, including fast radio bursts, which I will talk about a little bit more later, gamma ray bursts, which I probably won't talk about, and soft gamma repeaters. And basically, all of these phenomena are thought to arise from outbursts that release magnetic energy that is then processed into high-energy radiation. Properties, I'll talk about them a little bit more. Spin periods, P, when they are known, are of order seconds. Time derivatives of the spin periods, P dot, that's a dimensionless number, tends to be about 10 to the minus 11 seconds per second. So following the practice actually from radio astronomy, you get an estimate of the age, which is sometimes called the spin down age, and for periods of a second and period derivatives of 10 to the minus 11, that's 1,000 years, roughly. From these observations and a model, you can deduce the strength of the dipole field at the surface. And you get a derived value of 10 to the 14 Gauss. Okay, this is not a direct measurable, it's deduced. And I'm happy to explain, why people believe that's a reasonable number. Okay, so I made a table. Well, I stole a table of from the Australian National Telescope Facility, where you can look up basically every radio pulsar. These are the ones with the largest dipole field strengths, so the 18 largest. I basically searched for everyone with a dipole field strength greater than 10 to the 14 Gauss, and here they are. You can see that the spin periods are in the range of seconds, okay? And the deduced ages, in this case, which is a little bit anomalous, because it has a 76-second period, except for that one, thousands of years, perhaps even hundreds in a couple of cases, and maybe 10,000 years. Okay, so by the reckoning radio astronomers would use, these are young objects. Not all of these, in fact, I think only a small number, a small fraction, maybe one or two, show outbursts in high energy. There's a completely complementary compilation, which you can find at McGill University, Vicky Caspi and her group. These are objects that are largely discovered in X-rays and gamma rays. Vicky has made her career in part finding phase coherent timing models for these. And you can see in many cases, well, in all cases, the magnetic fields, the dipole surface fields, except for this one, except for, go back. Having trouble getting back to this. There we go. You can see that, except for this guy, the surface fields are all 10 to the 14 Gauss, and the ages are in the range of kiloyears. Okay, what distinguishes these objects? As I said, they have an enormous amount of magnetic energy. Unlike ordinary radio pulsars, the ratio of the rotational energy, just a half times the moment of inertia times the spin frequency squared, over the magnetic energy, basically b squared times some effective volume occupied by the field, is less than or of 1. In the ordinary radio pulsars, that inequality is reversed. There's more rotational energy than magnetic energy. Here, it's the opposite. Also, you can estimate basically the ratio of magnetic energy to gravitational energy. I prefer to think of it as the magnetic pressure divided by the central pressure in the star. And that's a small number at 10 to the 14 Gauss. But I'd like to point out to you, it goes up like the square of the energy. These are reasonable radii. M1.4 is the mass in units of 1.4 solar masses. That's a pretty reasonable neutron star mass. R10 is the radius in units of 10 kilometers. All of the neutron stars we know have radii perhaps 11, 12 kilometers where they've been deduced. The moment of inertia, basically a solar mass times 10 kilometers cubed, and that gives you 10 to the 45 in CGS units. And you can see this ratio goes like 1 over the period squared times the magnetic field strength squared in units of 10 to the 14 Gauss. So for somewhat stronger fields and slower rotation, you can get a pretty small ratio, so the rotational energy can be much less than magnetic energy. Magnetic distortions are typically of order the magnetic energy over the gravitational energy, so not big. Again, stronger fields, bigger distortions. The distortion is 1, this is a well-known number, for magnetic field strength of order 10 to the 18 Gauss. And people from time to time have done models for the structure of such objects, and they're pretty funky. You can even get donuts. Okay. So throughout this talk, I am going to mention some characteristic magnetic field strengths that are important for the physics. So one of them is, one of them is called the QED field. Now I'm going to warn you. So two of my former students are here, Roxandra and Tanya Rockland, and both of them know that I am the worst typist in the world. Okay. In junior high school, something probably doesn't exist here, but 8th grade, I got a negative score on a typing test. Okay. So I try to avoid typing as much as possible. So it's not that I'm a fancy theoretical physicist. It's just that I put in all the H bars and C's. They would have randomly chosen powers. So I'm going to set them equal to 1. So this is the Larmor frequency, and if you multiply by H bar, i.e. 1, and set it equal to the mass of the electron times c squared, that is mass of the electron, you get about 4.4 by 10 to the 13 Gauss, which is a little below the typical field strengths of magnetars. Now, the core of a neutron star, as some of you probably know, contains a proton superconductor. And in order for magnetic flux to penetrate the core, you need to have field strengths bigger than the first critical field strength. Hc1, P Fermi P is the Fermi momentum of the protons. MP star is the effective mass. In nuclear matter, protons behave as if they have a mass below the mass that you're familiar with from textbooks. And this number is about 10 to the 15 Gauss. Kappa is a dimensionless number. I can explain it later if you want to know. It has to be bigger than 1 over the square root of 2 to get a type 2 superconductor. Okay, so that's the first critical field. Somewhat higher is the second critical field, which is where the magnetic field is strong enough to destroy the superconductor. And that's more like 10 to the 16 Gauss. Here, delta P, you can think of, is the gap, the superconducting gap, or you can think of it as related to the critical temperature. The proton gaps in the core of a neutron star are typically of order MeV, and the Fermi momenta of order 100 MeV. Now, there's one other field strength that you could look at, which is when the magnetic moment interacting with the magnetic field has an energy bigger than about an MeV, which has two interpretations. One of them would be the mass difference between a neutron and proton, and the other would be superconducting gap, and that's pretty gigantic. Okay, about 10 to the 17 Gauss. Okay, so these are various characteristic field strengths that will appear, and I will often take, for reasons that I'll get into shortly, I will look at magnetic fields pretty close to HC2. Okay, the field strength that destroys the superconductor. All right. Now, observations at best probe the surface magnetic field strength of a neutron star. What about the inside? Do you have any probes of that? So an example, which I will talk about, is long period precession. There are several cases, and I'll talk about two related to fast radio bursts, where you see long-term variations in the arrival times of events from the neutron star that are quite regular. Okay, there are some radio pulsars that show this, and there are some two, actually as of yesterday, maybe three magnetars that show it. So the precession period should be the spin period divided by the magnetic distortion, and that could be 100 days for a 1 second rotator if the distortion is about 10 to the minus 7. And 10 to the minus 7, there shouldn't be a 10 there, typo number 1. 10 to the minus 7 is what you would get for magnetic field strength of order 10 to the 15 Gauss. So I should have gotten rid of the 10. Okay? This is, this ratio depends on what components there are of the magnetic field, what components there are of the magnetic fields, what its geometry is, and also the stellar density profile. So it's not simple, but roughly speaking, 10 to the 15 Gauss magnetic fields would lead to the distortions that you need for a 100-day spin period. Now, what is the evidence for this? So there are two, and that I consider reasonably solid. CHIME, which is actually an experiment that's supposed to be looking for 21 centimeter radiation from the epoch of reionization of the universe, actually turns out to be a really good way to find fast radio bursts. And they have found quite a few. This one appears and disappears regularly with a roughly 16-day period. So you can see it's not always on. CHIME is not. The new CHIME, the CHIME with outliers and so on, will be more sensitive, and we'll see a lot more of these outbursts, and so they can continue to study whether it's appearing and reappearing on schedule. Okay. There's another one, FRB. This is the date it was discovered, 2012. It's been around for a while. That also appears and disappears. And it does so. These are actually old data But you can see that there are many times when it appears and then it's not seen. And the magnetar, well, the fast radio burst appears to come back on schedule every time you look. So the data I'm not showing here, so I couldn't find a good graph for it, was from the FAST radio telescope in China, which sees hundreds of bursts from this object per day. And it's a gigantic receiver, a gigantic dish. And it reappears on schedule every 160 days or so. Okay. Now, one problem with ascribing this to precession is there's absolutely no hint of a spin frequency. Okay. And this, you might say, well, you just don't have enough data. But from FAST, you really should be able to see the spin in a day. Okay, 1 day of observation, we don't see it. This is the calculation we did at Cornell. At random, you would expect, this is a Schuster periodogram, for those of you who want to know. It's similar to Loam-Scargill, some other people may like. We looked at a pretty broad set of candidate spin frequencies. Only a few are above the line where you might expect one. So, you know, there are a couple. And there are no harmonics of those frequencies. So it appears there's no spin frequency. Okay. The FAST group has actually done this more rigorously than what we did, and reached the same conclusions. Okay. So one of the questions then is, if this is precession of a spinning magnetar, why don't we see the spin frequency? Okay. I don't have an answer for that. I wrote a long paper that did, and I'm not going to really talk about that much. Now I'm going to give you another argument. It's a little bit more theoretical. So I think I mentioned this during the panel discussion. I didn't give myself any credit, but there is a strong argument that neutron stars, that superfluid neutron stars cannot precess. Okay, and you know, I contributed a little to that. It originated with Jacob Shaham in the 70s and Bennett Link in 2003. So it's not a new result. So the core of a neutron star has neutron superfluid and proton superconductor. In the neutron superfluid, all of the rotation is contained in vortex lines. And in the superconductor, all the magnetic flux is in flux tubes. These are very small objects, well-known structure. But something's a little bit unusual is there's a phenomenon called superfluid entrainment, which I'd be happy to discuss with you afterwards if you want, which charges up the vortex lines. Okay, so the spinning vortex lines entrain some of the charged superfluid, and therefore the vortex lines acquire a charge. And by having a charge, actually a current, they can attach themselves to proton flux tubes, which turn out to be way more numerous in the crust. And the upshot is that the circulation associated with the vortex array freezes in the co-rotating frame. Okay? All right. And the result that Shaham first got is that, yes, you would get precession, but the precession period would be the spin period times the ratio of the total moment of inertia to the moment of inertia of the part of the fluid that contains pinned superfluid vortex lines. So what that means is that for a precession period of 10 to 100 days and for a spin period of a second, you would need almost total unpinning. Okay, only a part in 10 to the 7 of the moment of inertia could be pinned. If you want to prevent, if you believe that spin precession, that precession of a neutron star is what's causing 16 and 160-day periods, then to prevent the core superfluid everywhere, superconductor everywhere, you need a magnetic field strength bigger than the second critical field strength, so greater than about 10 to the 16 Gauss. You can also prevent the core superfluid everywhere. So my definition of everywhere is at most a part in 10 to the 7 where you do have pinning. If you have temperatures bigger than about 10 to the 9 degrees, that's not thought to be the case. In the crust, you can prevent crustal superfluid everywhere with 10 to the 10 degree temperatures, which you might have for a few seconds after the neutron star formed, but not after that. Certainly not for 1,000 years. If you want to prevent crustal superfluid in the magnetic fields, you can do that with magnetic fields stronger than about 10 to the 17 Gauss. That would actually distort the structure of the crust of the neutron star very significantly. It would form a different kind of crystal, it turns out. And as far as I know, this is unstudied, or studied only once. So you need strong magnetic field everywhere. As people like Tanner can tell you, it's hard to arrange that with the simplest magnetic fields, which would be poloidal plus some toroidal field. There are big regions where there basically wouldn't be a strong magnetic field. So that's complicated. So you need strong B everywhere. It might be that you have random turbulent fields. That would not be inconsistent with models of magnetars, but it would constrain their ages to be less than a few hundred years. And the reason is that ambipolar diffusion, which allows magnetic field to seep out, would basically happen on timescales like hundreds of years. Okay. That's also an old result due to Reisenegger and Goldberg. Okay. Oops. Right. And so the effect of strong B fields on the cross. Okay, so the requirements are you need misaligned poloidal and toroidal fields. People have looked at models of that. You need the field to basically fill the entire star, which generally requires an additional component disordered. I don't know if any of that can be stable. Okay, neutron star magnetic fields are notoriously unstable. Tanner can tell you he worked on this. Now, alternatively, it could be these long periods have nothing to do with precession. So, you know, in interest of being totally truthful, it's thought that the long period variation that is seen in a few radio pulsars probably is some unusually regular behavior of the magnetosphere of the neutron star, which people basically just hand wave that. Okay. All right. So why don't I pause here for questions about halfway through? Questions? Comments? Yeah, Miha.
These things are rotating quite fast, so the total magnetic energy is extraordinary.
I'm sorry.
These things are rotating quite fast.
Second.
Yeah. So what?
Maybe 10.
And having the magnetic energy comparable with the kinetic rotation energy is significant.
Yeah, that's what I said on one of the first slides. The magnetic energy is actually greater than the rotational energy, which is not what you have for usually in radio pulsars. Usually the opposite. Okay, Jordi?
Yeah, just wanted to ask if you could remind us. So initially you mentioned some values of the magnetic field where your characteristic processes happen. So when the alarm radius is equal to the mass, is this
of the electron, yeah.
4 times 10 to the 13 Gauss.
Yeah.
Then what is the process that you expect to happen at that above that field?
Well, in vacuum, you have to worry about the permittivity of free space. And so there are a couple of things that can happen. But that's in vacuum. I'm not talking about that case. So outside the neutron star, there are processes that are very important that actually can happen even a bit below this magnetic field strength, such as single photon pair creation. You know, usually you need 2 photons because of energy and momentum conservation to create E plus E minus pairs. But in a strong magnetic field, the photon can come in, interact with the electromagnetic field, which acts as a sort of virtual photon, okay? And you can produce pairs that way, okay? So that's probably the most important one. But basically all of the electrodynamic processes would be affected. You also get important effects on what the polarization modes of photons are. Because you have basically a dielectric constant of the vacuum that isn't, or I guess it's more magnetic susceptibility or magnetization. That's not what it usually is, which is 1 in some units. Okay, so that affects the polarization modes and how they propagate. There's another.
Yes. So I guess all your previous arguments are trying to, I suppose, go against the pinning, right? But there are also not many observations that require pinning in neutron stars. No, if anything, maybe glitches, right? Yeah. So and even the explanation for glitches is, as I would also put it, in a hand wavy.
Well, yeah. So, okay, I'll grant you that.
So I'm just saying that this image.
I'll grant you that because I've rejected papers by famous authors.
Okay. And also, of course, some of the nuclear physics inside the unit to understand these things like gaps. And I would argue, you know, a lot of systematics having worked on this in the past.
Yeah. So I would say in the core, and perhaps this is what you've worked on, the main complication for both the superfluid gaps of the neutrons and the superconducting gaps of the protons is the presence of other neutrons and protons. So the many body effects are quite complex, and I suspect the calculations have never gone beyond, 3 body effects. Okay. However, as time, there are other effects, by the way. Believe it or not, relativistic kinematics matters, and that has changed gaps over time, actually lowered the neutron gaps, as it turned out. Okay, so yeah, it's complicated. None of this is simple. The old war horses who worked on this did their best. And now there are young war horses who are trying to, improve the calculations. Okay, but it's not simple. I mean, relativistic many-body theory, that ain't easy. Causality is a big problem for those. I don't do it, it's too hard for me. I'm a consumer or abuser. Okay, more questions? These are good. Okay, so now I'm going to talk about things I sort of know. So, in fact, I don't know all the answers to them expected. So I'm going to focus on the outer crust, which is densities less than about a few by 10 to the 11 grams per cubic centimeter. That's about 1,000th of nuclear density, which is roughly the lowest density of the core. In this region, normally, free electrons, so that density is called neutron drip. Below that density, you don't have free neutrons. So the pressure is basically all due to freely moving electrons, okay? And electrostatic effects, which I'll talk about later. So what you have are free electrons and weird nuclei in this region. Can even be more complicated, I'm sure some of you know. And when I say weird nuclei, so at drip, I don't know, the charge might be 35, and the mass might be 140. Now, you won't find that in a table of nuclides, so they're weird. At 0 density, you would expect iron. Okay? Just to give you a point of reference, electrons are relativistic above about 1 million grams per cubic centimeter. So there's a lot of space between where electrons become relativistic and where you start getting free neutrons. There's a factor of perhaps 100,000 in density. So Tanya showed equations, so I'm not ashamed to do it, but mine are a lot simpler. So hydrostatic balance would then be minus the gradient of the pressure, which is all due to electrons, plus the gravity force is 0, but in a magnetic field, you have J cross B. Okay. J, and for now, is the curl of B over 4 pi, just Ampere's law. I left out the C, I know. And del squared phi is, might have a minus sign error of 4 pi g rho. Okay, I think I have the minus sign right. Now here's the concern. B squared over 8 pi can exceed the electron pressure very easily in this region. This is a problem, by the way, that's well known from ordinary stars. Magnetic stars, if you go far enough out, the magnetic stresses are more important than the pressure. And to my surprise, not much work has been done on this. So I'm starting on it in the super weird region. Okay. All right, so I'm going to go through this quickly. So let's suppose you wanted to make an axisymmetric field. So you would have a poloidal field with, field lines. This function, psi, counts field lines. That's how I like to think of it. It's a label that is fixed along each poloidal field line. Curl of a poloidal field is toroidal. So you get a current, it's toroidal. You also have a toroidal magnetic field that has a poloidal current. If you don't stop it from happening, you get a toroidal force, which would make the star want to accelerate around the magnetic axis. And to get rid of that, basically, you can think of it as you have a current loop, you have a toroidal field and a current going through it. And the current is just a function of this stream function. Okay, so there will be field lines that penetrate the circle, and at each circle, there will be some function which you don't know a priori. But you can try to constrain in various ways, particularly stability. You have ordinary hydrostatic balance along the magnetic field. And so under the right circumstances, some function of the electron chemical potential plus the gravitational potential is also just a function of the field line label psi. And people have studied this problem forever. Okay. All right. So you try to solve this. You match to something you think you know outside, either force-free or a pulsar magnetosphere type solution. It's a numerical problem. It's not analytic. And this matching is not trivial. There are a number of questions. I'm just beginning to work on this with my most recent student, Peter Rao. We don't know the shape of the boundary a priori. It's magnetic dominated. And we certainly don't know about stability, as Tanner will be happy to tell me I don't know anything about. Now, in the crust of a neutron star, magnetohydrodynamics is a little bit different. It's what's known as electron MHD. So in ordinary magnetohydrodynamics, you have a fluid flow, and the field is carried along with the fluid. So that's fluid velocity V. In the crust of a neutron star, the nuclei are not mobile. Okay, it's like that table. Okay, at best it'll form a crystal. So it's the electron current that carries the field. It's also something people have talked about for years. For steady state, Faraday's law would require that the cross product of basically the electron current and B is another function of a scalar potential, perhaps the same scalar potential that counts the poloidal field lines. Okay? You can get waves in time-dependent case, which have, they're called Hall waves. They're sort of spirally type waves. And they actually have very low frequencies, so depending on the scale. So if you had a wave, a Hall wave on the scale of the crust of a neutron star, it might have a period of 10,000 years. Okay, that's pretty long. All right. Okay. Now, I'm going to switch gears into something that, as far as I know, only my former student, Peter Rao, and I, and a numerical relativist named Elias Most are at all interested in. Okay? So if you don't want to listen, don't listen. But you should. Landau quantization. So first I'm going to tell you why it matters. So what that means is the electron orbits are quantized in a magnetic field. And I'll explain that on the next slide very crudely. So what happens is the electron pressure becomes a function not only of the electron chemical potential and temperature, but also of the magnetic field. Okay? And hydrostatic balance looks the same, but J is now curl of H. And the magnetization is the derivative of the electron pressure with respect to B. I'll show you some results for that. And so you get a magnetization current, which is here. So it turns out M over B is small, okay? But d by dB of M over B can be bigger than 1. So this can be a really big current, okay? And of course, Faraday evolves the field. All right. So very quickly, physics. Non-relativistically, you know, electrons move in circles around magnetic fields, so classically. Quantum mechanically, the perpendicular energy is quantized. Okay. So E perp is the Larmor frequency times an integer plus a half. And this is for a spinless particle. I'll put spin in a minute. Relativistically, what you get is that the relativistic energy is the square root of the mass of the electron squared plus p parallel squared plus 2EB times an integer. Okay, and mathematically, the way you get this is what I've outlined on this slide, namely, from a mathematical point of view for a spinless particle. Basically, the equation for the Dirac equation is h squared equals e squared, and h squared looks just like the non-relativistic quantum mechanics version multiplied by the mass. So a couple of things you can see. One is that for a Fermi energy of the electrons, E Fermi E, there's a critical, if you like, p parallel, which can go to 0 at high enough mode quantum number. Okay. All right. So the pressure is the 0B pressure plus a correction. The density is the 0B density plus a correction, and so on. The calculations tend to depend on two parameters. One of them is the number of filled Landau levels, which is this ratio. And at 10 to the 16 Gauss, that's like 12.5 at the densities of interest. And even at B equals BQ, it might be a half as you go out. So not many. The temperature smooths out these levels. The ratio that comes into play is KT divided by H bar omega B. And I think K Boltzmann equal to 1 here too. And that number tends to be small. So in textbooks, when you read about magnetized, Landau quantization and magnetized situations, they take the limit that nu f goes to infinity, but the temperature also is much bigger than the level spacing. Neither of these holds in a neutron star. So here's the pressure. I didn't subtract off the smooth stuff. Those of you in the front, Roxandra, can see that there are wiggles. The magnetization looks like this, multiplied by 100. So it's of order E squared, as I said. But here's the derivative. Big. These oscillations have a name. They're called de Haas-Van Alphen oscillations. The textbook limit, if I plotted it here, you wouldn't see it. Okay, 10 to the minus 2. To blow things up a little bit, I can plot H versus B. And it looks, generally it goes up linearly. But because of the derivative of the magnetization, it goes down and up, down and up, down and up. All of these down portions are unstable thermodynamically. You only want the up portions. So at each one of these, you perform what's known as a Maxwell construction, just like you would in a gas of particles with finite size, like van der Waals gas. And so there's a jump in B. H is continuous, but B is not. So you get a domain wall. This is the Maxwell construction condition. This turns out to be the condition that there's no magnetic stress. And it follows from this condition as well. You can see that here too, where I plotted B versus H. You want to go across, up, up. There are jumps. Okay. Okay. The spacing between these jumps is not that big, could be a meter. B jumps by a small amount, but nevertheless it jumps. And when you form these domain walls, there might be some energy release. People have talked about that. Although Maxwell construction avoids the largest possible susceptibilities, large values can still arise. Field evolution at low temperature, this is sort of the limit. The magnetization largely depends on P Fermi squared over 2EB. You get current densities due to gradients in both the field strength and the density. A field with curl of B equals 0 will evolve because grad of B is non-zero. Even a uniform field evolves if the density is non-uniform, which is true of everything. And ohmic heating is enhanced. So I'll show you that. That's one numerical result from this paper, which had a lot of other things. This axis tells you how much Landau quantization enhances the rate of ohmic dissipation, rate of ohmic heating, compared to what you have without it. And you can see it's at least a factor of about 2. Okay, depending on parameters, so it's not small. Okay, now at low enough densities, the electron gas will become one-dimensional. Okay, that's when it happens. This is the electron density is this. It goes like P Fermi, not like P Fermi cubed. That's the pressure. And in addition, you have electrostatic pressure, as you always do, which is negative. Okay? In ordinary gas of degenerate electrons and nuclei, you get densities like the density of that table, 1 gram per cubic centimeter, where the two cancel. Okay? Not so in this one-dimensional gas. The pressure goes to 0 at roughly 100,000 grams per cubic centimeter. This is a lot different than what people have talked about in the past. Okay. So I'm going to summarize. What are the field strengths inside magnetars? Likely stronger than at the surface. Outer layers, b squared over 8 pi is greater than the electron pressure. Hydrostatic balance is modified. Do you end up with force-free fields? Do you end up with winds? Something I'm working on right now. Landau quantization matters. There's a large magnetic susceptibility. The derivative of the magnetization with respect to B is big. You get magnetic domain walls and enhanced ohmic decay. The 1D gas is inevitable at low density. This is not a new result. It's just I've amped up the magnetic field. And there's even further modification of hydrostatic balance and 0 pressure at fairly high density. So not a gram per cubic centimeter, more like 100,000 or even more. Okay, thank you.
Thank you, Ira, for a very nice talk. Okay, questions, comments?
Thank you very much for a very nice talk. I have a non-expert question. So do we know the equation of state when magnetic field is such a strong?
Yes and no. So I sort of skimmed over it, but the most important effect is that you include the magnetic quantization in the electron Fermi-Dirac distribution. That is well understood. There may also be effects on nuclei. People have looked at that. People, this is not a problem that only I work on. I'm thinking of Nicolas Chamel, who's, I forget exactly, he's in Belgium, and Alex Patekin, people like that. Those effects don't actually appear, as I recall, to be terribly big. Okay. There are other effects that people worry about in the cross that may or may not be well understood. One thing I will say is, I didn't talk about this at all. It's known, or it's conjectured, that, so I talked about the crust with nuclei, intentionally went far out where things are simple. However, people know that nuclei have different shapes, okay, as you go to higher densities, and even turn inside out, okay? So that's been conjectured for a long time. It's probably right, okay? And magnetic fields might have an effect on that.
Okay, other questions?
The nucleus turned inside out.
Hmm?
The nuclei turned inside out.
Yeah, so instead of having a spherical nucleus with nuclear matter inside, it can become, and neutrons outside becomes energetically favorable to have neutrons inside and nuclear matter outside.
And another thing,
That result is 35 years old, actually.
this may show my ignorance.
Most people don't know about this stuff.
You mentioned the whole wave
Yeah,
with a period of 10,000 years.
well, that's the lowest period, but on smaller scales, faster.
10,000, like these are objects that are, these are 10-kilometer objects that
Right.
rotate about once a second.
Right.
It surprises me to see something with a period of 10,000 years when the thing rotates once a second. Am I?
Has nothing to do with
wrong?
rotation.
I know it can't have.
Yeah, it basically is a spiral motion. I think along magnetic fields typically. So it's a funny kind of wave. But yeah, the periods can be very long if the wavelengths are kilometers, but it goes like 1 over the wavelength squared. So it can be much smaller. It could be faster. So I didn't show you, and you know, you should be thankful, work that Peter Rao and I did on the evolution of magnetic turbulence under these circumstances, which is also very complicated. But superficially, the answers turn out to be simple. Okay. Yeah, there was another question or two.
Yeah, I had a question about this last point on the one-dimensional electron gas. So I guess one was conceptual, trying to understand why it turns one-dimensional. I suppose, is it along the magnetic
Yeah,
field axis?
because the number of filled Landau levels goes below 1.
Right.
Okay.
And
Eventually that happens because it's proportional to the Fermi momentum
sure,
squared.
yeah, so at low enough.
So
that
at
field,
any
you always
magnetic
see-
field strength that happens, what's a little bit, you know, you may have noticed on my slide that it says where this happens is fairly insensitive to B. And you can kind of see that here's 10 to the 16, here's 4 by 10 to the 13. It's only in these units a factor of about 3. Now, NB is proportional to B, so you know you get an additional effect due to the magnetic field. But in these units, N over NB, where you get this intersection only goes like something like B to the 1/5. Okay, so it's pretty soft.
Your suggestion is at some point there's going to be hydrostatic instability. at the
Yes,
surface
yeah.
because the magnetic field. You know,
Yeah,
if the electrons are not there anymore to provide the pressure, you'll.
Well, they are there, they're providing pressure, but the electrostatic pressure is balancing it just like in the table. Right? I mean, here you get 1 over the Bohr radius cubed for the, you know, the electron density where it happens. But here it's different. Yeah. It's pretty wacky. Yeah. But I actually think this is also something that people wrote about a long time ago. I remember an old paper, not on magnetars, but ordinary radio pulsars by my colleagues at the time, Dong Lai and Stu Shapiro, where they found a similar result, didn't really say much about it. Okay. But I think for modeling the structure of a neutron star, it kind of matters where the pressure goes to 0. Okay.
Okay. Any other questions?
I was wondering if whether you could Yeah. Comment a bit more on the amplification of the ohmic dissipation and how it depends on the value of the B field itself, because maybe I missed it, but it seems to go, it
So-
seemed to me it went the
Sure.
other way round with respect to what I would naively expect. But
Yeah, so it goes like J squared over sigma. And J depends on the magnetic susceptibility. Okay, so that's where the B field dependence can come in. But the susceptibility always becomes big so I'll go back.
yeah,
At places, so I drew these dashed lines,
Yeah, I was
which
wondering
are
if-
places where you get integer values.
I was thinking about the next plot you show where you
Yeah.
have the amplification factor.
Oops, that one.
Yeah.
Yeah.
So for
So we made
for a
up,
weaker
we made
field-
up B field models. Yeah, go ahead.
yeah, for a weaker field, then you have more amplification for the
Ah, that's what you're-
temperature, and then it turns around.
Yeah, well, there are a couple of parameters also in the length scale. So the weakest field has the shortest length scale plugged in. So it's not entirely just B field strength. There are a number of things that are happening here. So I didn't say what this calculation was.
Of course.
So you can see here, it's actually inverted, unfortunately. The calculation had a resolution of 192, which is actually L over delta L, the spacing of 192. And we evolved the field. Among other things, you get small scale field. So just like I said, all you need is a density gradient, but a gradient in field strength will take large scale field and knock it into the small scale.
Okay, so
And that
everything
helps
is
with the
linear, and
dissipation.
so okay, thank you.
So length scales matter. And you get a whole turbulent spectrum here. This includes ohmic decay and the
Hall effect.
Hall effect.
Okay,
Okay.
yeah, it makes sense now. Thank you.
Well, you
Well,
know, I mean,
It makes
exactly.
sense that it doesn't make sense.
But
No.
qualitatively, I hope that, those are the
Yeah.
important effects.
Thank you.
You produce a lot of small scale field. Okay, that's enough.
Yes. Next.
Thank you for paying attention and sticking around despite no cookies.
Yes.
By the way, Roxandra is buying for everyone cookies. No, she isn't. So, yeah, thank you.
Okay, let's thank Kyla again.